Hey everybody, welcome back. Mr. Smith here. In today's slide deck, we're going to address the problem that exists at the beginning of the Giancoli Chapter 30 unit on nuclear physics, and it has to do with the density and the size of the nucleus. So you'll remember that Rutherford is blown away by the idea that all the positive charge in an atom could be consolidated into this thing called the nucleus, but it's the only way to explain the fact that most alpha particles just cruise straight through the gold, and every once in a while one of them ricochets right backwards. So we're going to begin by talking about two kinds of straightforward conversions so that units don't bog you down. But I will say that being attentive to units when you're dealing with nuclear physics and atomic physics is hugely important. So when we're dealing in the world of atoms, we use a thing called atomic mass units for mass. So one atomic mass unit is equal to a really tiny number of kilograms. So 1.66054, and there's more decimals after there besides if you want them to. So this is one conversion that you're going to want to have handy and write it down, use it, save it. You'll need it in the future. What we're being asked to do in this problem is to convert the mass of a carbon-12 atom into units of grams and kilograms. So why carbon-12? Well, there's a reason I picked it. Carbon-12 is the only isotope on the periodic table that has a mass of exactly 12. So what did scientists do? Carbon-12 has 6 protons, 6 neutrons, and 6 electrons, but carbon-12 is really common in nature, and it's a very stable isotope. So what you can do is dig up a shovel of carbon-12, and they assigned it a mass of exactly 12, and then assigned the mass of the protons, neutrons, and electrons based on that. So anyway, to do the problem is dead easy. So we'll take 12 atomic mass units, and to convert those things to the world of that you and I live in, we'll convert it to kilograms. 1.66054 times 10 to the negative 27 kilograms in one atomic mass unit. And we get this really tiny number. Also, it's 1.99 and change. What is it? 26 times 10 to the negative 26 kilograms. Okay? So I trust that you'd be able to convert that to grams also. If this is a problem for you, let me know, but I would worry about you if it was a problem. This is going to be 1.9926 times 10 to the negative 23 grams. Okay? All right, so that conversion is up and out of the way. Pay attention. If you're in atoms, you're probably in the world of atomic mass units. If you're in the world of the huge stuff like you and me and nuclear power plants, then you should be dealing in kilograms. Okay? Another thing that we're going to see in just a second is the need to convert kilograms per cubic meter into, which is a real physics unit for density, into grams per cubic centimeter, which is a very common chemistry unit of density. And so because nuclear physics has history in both areas, you're going to get both of these conversions going on. So let's just start with 1 kilogram per meter cubed. And you'll notice that what I do is I write it with a clear top and bottom. I think that's really important when you're doing conversions. And so we'll just do these one at a time. I think it's easy to convert from grams to kilograms and do that first. So we'll do the conversion that we didn't do above right here. And then that part's all set. And then what I'm going to want to do is get from meters cubed, so I'll put meters here, centimeters there, and do the correct thing with my numbers. But just remember, in this derived conversion, I have to do this 3 times so that the metric units actually cancel. So meters cubed cancel. And what happens is the conversion factor comes along for the ride. And so 100 cubed is actually 1,000,000. And so what we end up getting here is that 1 kilogram per cubic meter is equal to 1,000th of a gram per cubic centimeter. Or to flip it around backwards, 1 gram per cubic centimeters of density is equal to 1,000 kilograms per meter cubed in density. So these just become another conversion factor you can use. Okay, so now actually to the physics. In Rutherford's experiment, I wanted you to appreciate by looking at this slide that he took classical physics, so the physics of, say, pool balls clattering off of each other, and really extended it to a very, very sophisticated degree. What was going on was that we had positively charged alpha particles approaching a positively charged nucleus and then ricocheting. So what's going on here is the Coulomb force. F equals K, Q1 times Q2 over distance squared is the force that's keeping the alpha particle at bay and keeping it from pummeling right through the nucleus. So based on the proportion of alpha particles that scattered and the average angle of scattering, Rutherford derived this very, very complicated expression where you have N is the density of per unit volume of gold atoms. You have L is the target thickness, Z is the atomic number. So this gets into how many atomic cores were there inside of the target, Coulomb's nucleus, etc. And what he did is we derived from this scattering angle a way of figuring out the size of the nucleus. And he was blown away, absolutely shattered when he got the answer. And you'll see why too. And you should be incredibly impressed by this. It's just mind-boggling. So here's our expression we're going to work with. This is an empirical relationship, meaning it's derived from the experiment. This means approximately equal to. So for all atoms, there's approximately a solid rule that says that the radius of the nucleus is 1.2 times 10 to the minus 15 meters times the atomic mass raised to the 1/3 power. Okay, so we're going to use that in the following question and work you through all the steps you'll need to be able to do these calculations. So to begin with, we're being asked to estimate the diameter and volume of a nucleus of gold 197. And then in the next slide, we'll go and get the density of it and then figure it out compared to gold's atomic density. How dense is the nucleus? So first things first, this formula is pretty straightforward. We're just going to go ahead and use it. They'll get the radius, and we'll replace that with an equal sign. We'll just say 1.2 times 10 to the minus 15 meters times the atomic mass. Well, gold 97 has a mass of 197. So let's take atomic mass of 197 and raise it to the 1/3 power and put that into our calculators. And what we get is a pretty small number, 6.982 times 10 to the minus 15 meters. Okay, and minus 15 meters, by the way, is called a femtometer. So around 7 femtometers is the size of a gold nucleus. Now, to get the volume of the gold nucleus, what we're going to do is pull out an oldie and goodie from geometry. The volume of a sphere, which is what we're going to assume that the gold nucleus is 4/3 pi times the radius cubed. Oh, by the way, right? If you caught me, good for you. I didn't actually answer the question about the diameter. Diameter is 2 times the radius. Already far enough into this slide, I'm not going to bother to write it down. But anyway, multiply by 2, it should be like 14 femtometers, right? Anyway, to get the volume, we're just going to go ahead and plug in 4/3 pi times the radius that I just figured out, 6.982 times 10 to the minus 15 meters. And this, I think, is where if you're paying attention as a sentient human being, you should really be blown away. The volume of the nucleus is the smallest thing, 1.426 times 10 to the negative 42 cubic meters. It's just the smallest number I've ever seen in all of looking at physics. It's insanely, insanely small. And so when we talk about the idea of black holes, or we talk about the power that it would take to constrain all those protons in a space that small, you could really see where this area of physics became a holy grail to understand and to exploit for experiment. The physics, the size and the power and the density of stuff is just mind-boggling. Okay, so anyway, we've got a size for the volume of the gold nucleus. Let's go ahead and move that forward, and we're going to go ahead and do the next step. So to get the density of the gold nucleus, what we have to do is just use our formula for density. Density equals mass over volume. Okay, well, we can do that first step first. Let's get the mass of the gold nucleus first. So the mass of the gold nucleus is just going to be 197 about atomic mass units, right? So we'll do the conversion we just did a second ago times we'll just call it 1.66 times 10 to the negative 27 kilograms for every 1 U. And that ends up giving us a mass for the gold nucleus of 3.27 times 10 to the negative, and it's 25 in the kilogram department. Okay, so now we've got our mass. we just got the volume. Now we're in a position to go get the density of the gold nucleus. So we're just going to take our mass, 27 rather, times 10 to the minus 25 kilograms, and divide that by the unimaginably small volume, 1.426 times 10 to the negative 42 cubic meters, and we end up with this stupidly ridiculous number, 2.29 times 10 to the 17 kilograms per cubic meter. Okay, so we'll talk about black holes later, but that's a density that's a real number in the universe. That's the density of a gold nucleus, 10 to the 17 kilograms crammed into a cubic meter of space. That's unimaginable, right? So the metaphors for the nucleus are just so over the top. It's like taking all of the mass of Gillette Stadium and collapsing it into a marble on the 50-yard line. It's beyond that. So absolutely insane. So it really fuels the discussion about nuclear power and nuclear force and what's going on inside the nucleus that makes this kind of thing possible, because it's so astounding. Okay. Finally, let's just wrap it up and compare that density. 2.29. Let's get it one more time. 2.29 times 10 to the 17 kilograms per cubic meter. Well, that needs to be converted, doesn't it? So what we're going to do is actually employ our unit conversion, and we're going to multiply by, let's see, 0.001 grams per cubic centimeter over 1 kilograms per cubic meter. And it turns out that this density is 2.29 times 10 to the 14 of the units that we would commonly use when we're talking about densities in chemistry. So 2.29 times 10 to the 14 versus 19.3. Right, yeah. So this is the density of gold. You thought gold was heavy? Yeah, gold's nothing. The density of the gold nuclei, now that's a whole different thing. And this is what fuels the understanding that you should have about how empty matter really is. So final thought, what keeps you from pressing your solid fingers through the solid desk below you? It's not because either of them is solid. They're not. They're mostly hollow. What it is it's the skin of electrons around the wood desk or the plastic desk, and it's the skin of electrons around your being. And the fact that those electrons, because they're part of a structure, can't just run away from each other, that there's going to be resistance when they do that, that keeps you from passing your hands through tangible objects. But anyway, that's the step-by-step that you need to be able to do that early problem in Giancoli. Take care of yourself, bring your questions with you to class, and we'll see you soon. Bye-bye.